Okay, for Chapter 6. Chapter 6 really primarily has two main concepts and then a little bit of terminology at the start to go with it. So first, the big thing, the terminology really to worry about is all related to bonding and how different atoms bond together. The two big terms we used in the class a lot were first was the idea of electronegativity. This was the idea that there was a measurement that could tell us how much did an atom want to hold on to electrons when it forms a bond with other atoms. If you remember right, this trend is increasing as you go towards the right of the periodic table and as you go up on the periodic table. This means fluorine, which is in the top right if you don't count the noble gases, is our most electronegative atom. Whereas if you go towards the bottom left, towards atoms like cesium and francium, they are very low electronegativities. Now, you should also remember that based on these electronegativity values, we can define three different types of bonds. Covalent bonds, polar covalent, and ionic bonds. And which of these the bond is depends on how big the difference in electronegativity is or how small. So for very small differences, we have bonds called covalent bonds. In this case, the bonds are such that the electrons are just shared between the two atoms equally. Both get to have about the same amount of time with the electrons. It's like it's really half and half. We then have a middle point. That's polar covalent bonds. So these are bonds that have not really large electronegativity differences, but they've got larger ones than the ones that happen with covalent bonds. For these, the electrons still act like they're shared, but they start to act like an uneven sharing. One atom, kind of like a person if they're trying to share something between them, one of the atoms is going to get the electrons a lot more often than the others. This leads to a covalent bond where, if we draw a structure on it, it looks like it's actually got a polarity difference. What we mean by a polarity difference is it's like there's a little bit of charge on both our atoms. The one that has a higher electronegativity holds on to the electrons longer. They get a partial negative charge on them. On the other side, the atom that doesn't have a very high electronegativity value that's lower, it doesn't get to have the electrons as often, so it's like it's got a partial positive. And we write that, you'll notice sometimes we'll write bonds and they'll look something like this. The idea is that the arrow over here is towards the partial negative part of the bond. We draw this little symbol here. And over here, at the other end of the arrow, right here, this is going to be our partial positive side. If you notice also the side on the left looks kind of like a plus sign, right, that we're making with the end of our arrow. That's where the atom is, so that part of the bond is slightly positive, whereas this other side, the end of the arrow that's got the pointer, is slightly negative. Then we finally have ionic bonds as our third type. In ionic bonds, this means that the atoms have an electronegativity difference that is very large. This usually occurs between a metal and a non-metal. When we've got an ionic bond, that means that one of the atoms took electrons from the other. So, going back to our definition of electronegativity, if they have a high electronegativity, that means the atoms really like to have electrons when they form bonds. So the higher electronegative atom is going to take the electron entirely and create a negative charge. Whereas the other atom has to lose an electron, and now it is a fully positive charge. So we get something that looks like this. One you probably know of is you have sodium chloride. And with sodium chloride, what actually happens, it forms an ionic bond. Okay, stop that. I got to change. Hold my pen wrong. Where you have a sodium plus and a chlorine minus. That's what actually happens in the system, and they simply stay attracted to each other because negatives and positives attract. So the chlorine had a much higher electronegativity than sodium, so it took one of the electrons, and sodium lost one. That's what happens in ionic bonds rather than sharing. Okay, so now we have some language to talk about bonding. There are really two things we have to do with bonds. First, we have to write Lewis structures. So Lewis structures are just a way of representing, especially with covalent bonds and polar covalent, where the electrons in our molecule are. It also gives us a way to keep track of, okay, are we sure where all the electrons are in terms of everybody got enough? Because remember, you're trying, based on our rules, to fill up the octets of the different atoms. And depending on how you draw the Lewis structure, it may turn out the different atoms need to share more or less electrons to form a stable structure where everything is happy. Also remember that in addition to just drawing Lewis structures, this is also where we talked about resonance structures. That's where the atoms could share in different ways, so you had to draw different types of bonds. For example, in carbon dioxide, which we can draw here, the most common form we see is this right here, where the carbon has two double bonds, and the oxygens end up with 4 electrons each. But while this is the most stable form, based on formal charge, We could also draw resonance structures such as this one, where we had a triple bond and a single bond. You'll notice that I did not change where the atoms are. It is not a resonance structure if I change the carbon to be on the right and I put one of the oxygens in the middle. That is now a new molecule. You'll also notice that while I moved around the bonds, I still drew the same number of electrons overall. If I had more or less electrons, that would have changed my system. So it has to have all the same atoms in the same order. They have to be connected in the same way. The only difference here is that some of the electrons end up being in different places. So in this case, while both oxygens are still bonded to the one carbon in the middle, on the right structure, one of the oxygens is bonded, triple bonded, while the other is single bonded. Whereas in our more stable structure on the left, both are double bonded. Now you notice I said that one was more stable than the other. We know that's through formal charges, which I will show you on the next slide when we get to Lewis structures. We'll do some practice with those. But make sure you know what a formal charge is and how you calculate it. So then we finally have one more concept we deal with, which is what we call VSEPR. So this is going to be our electron and molecular geometries. This is the idea that based on the resonance structures, we can figure out what the shapes of our molecules are. And this was something where you just had to kind of learn a lot of them. That's what that big table in your text was on. But we'll go over some of these to make sure that you've got them down. Okay, let me clear this out. So let's talk about some Lewis structures. Clear, where are you? You were here somewhere. Okay, I just had to move slides and the ink went away. Okay, so for Lewis structures, we want to write a Lewis structure for the following molecules. If appropriate, we need to draw any resonance structures, and we need to use formal charges to determine if one structure is more stable than the other. So let's start drawing some of these. And remember, not all structures will have resonance structures. You'll actually notice a lot of these don't. So we're going to start with CH4. So the first step is we figure out what atom's in the middle. And we know that hydrogen can't be the central atom. That was one of our rules. So we have to have carbon in the middle. We then have to bond it to every other atom. We're only dealing right now with structures where we've got one center atom bonded to a bunch of different ones. Okay. We then have to figure out how many valence electrons we brought with the system. So you remember carbon brings 4 electrons. And then we had 4 hydrogens, and each is going to bring 1 electron. So that means we're going to get a total of 8 electrons we need to draw. So if we go through now, once we've drawn the skeletal structure, we count how many electrons have been used up. Each bond represents 2, and there are 4 bonds. So we've used up 8 electrons, and we are left with none left over. So we have to be done. But we need to check and make sure all the atoms are happy, or to see if we need to make any double or triple bonds or move stuff around. Each hydrogen only wants 2, and because each has a bond, it's got its 2 electrons. The carbon in the middle has 4 bonds, so it's got 8 electrons. So our CH4 is happy. We are done with CH4. So now we're going to move on to another atom, where we'll probably have to do some more, rather than just put some lines and be done at the beginning. So we have carbon monoxide. That's our CO. You'll notice that there are only 2 atoms. That means there isn't really a central atom. We'll just draw them like this. They can only be connected in one way. So how many valence electrons? We have 4 in our carbon, 6 in our oxygen, so we need to draw 10 electrons. And we currently have 2 showing in the 1 bond. So there are 8 left. So in this one, you could start wherever. It's going to turn out the same way in the end. I'm just going to start here. I'm going to put 2 electrons. It does not want me to draw dots. It thinks me doing that is me trying to right click. But okay, that's 6, so I've got 2 more. I put 2 on my carbon. But now we know that if the carbon only has 4 electrons, well, the oxygen has 8. But neither atom is an exception to the octet rule, so both need 8. So the only way to fix this now is to have sharing of electrons. Another important note about this is that the atom that is deficient, that means the atom missing electrons, can't be the one to start the sharing. Carbon has a lone pair, but if it shares it, it just gives oxygen 10. It doesn't add any to carbon. So you have to get the electrons from the atoms with enough to the atoms that need them. So we're going to take this lone pair here, and we're going to move it into a bond. So this will give us carbon with a double bond. But now we're only going to draw 4 electrons because 2 of them are now in a bond. But if you get to this point, you will notice that carbon only has 6 while oxygen has 8. So a double bond isn't enough. So we've got to share some more. So we're going to move these up here. We're going to make a triple bond. So we have carbon triple bonded to oxygen with 2 electrons on each, 1 pair. And that is going to be our structure. You'll notice that it does have a triple bond in it. Sometimes that means they're resonance structures. But here we only have 2 atoms and 1 bond. That bond can't go anywhere else. So we're done with our structure. We don't have to worry about resonance structures with our carbon monoxide. So that's our first 2 structures. So let's do some more. Okay. So now we're going to look at SO2. That's our third atom, or our third Lewis structure. So if we look up the electronegativities, we find that sulfur has a lower electronegativity than oxygen because it's lower, it's in the lower group, part of the group, even though they're in the same group. It's further down. So sulfur's going to be in the middle, and we're going to bond it to 2 oxygens. We do this, we've got to figure out how many valence electrons we have. Each oxygen gives us 6, and sulfur gives us 6. So we're going to get a total of 18, but we've already drawn 2 bonds. So that's 4 electrons. So we need to draw 14 more. So if you remember your rules, you start with the external atoms before you add any to the middle. So let's start adding them to our oxygen here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Both external atoms are now full. So now what we need to do is we need to see how many we've got left. And as you can imagine, 14 minus 12 is indeed 2. And with any leftover electrons, you always put them on your central atom now, once you filled up the external atoms. Please don't do that to me. Okay, so we check now, because once we've run out of electrons, we have to check to see if we've got enough on all our atoms. Both oxygens have 8, 6 lone pair electrons and 2 in a bond, so they're happy. But sulfur has 2, 4, it only has 6 electrons, so we're going to need to get some sharing done. It's going to have to get some help from one of the oxygens. So we're going to move one of these into a double bond. This will form oxygen with a double bond, like this. Now, this is where resonance structures start coming up. The reason for this is that there's no reason that this has to be the double bond on the left. We also could have had a double bond on the right. They're both equally likely here. Well, we have to figure out they're equally likely. We will in just a second. But they both could have happened. So we have 2 structures, and both are possible structures. So now we want to figure out, is one of these structures better than the other? We do this by calculating the formal charge on each of our atoms. So if you remember right, formal charge, I'm going to put this up at the top, is going to be the number of valence electrons in our atom. This is at the start of the whole thing. So, for example, oxygen is going to have 6 valence electrons at the start. You're going to subtract lone pair electrons. These are the ones we drew. You're also going to subtract 1/2 of the bonding electrons. So it only gets to count half of these. You could also just subtract the number of bonds if that makes you feel better, because since each bond has 2 and we're taking 1/2 of the bonding electrons, 1/2 times that would give you the number of bonds. But I'm going to do it this way because this matches the way I believe the text does it. Okay, so we can now calculate this for each atom in our system. So oxygen has 6 valence electrons. It's got 4 lone pair electrons drawn. This is the left oxygen. And it has 4 bonding electrons, 1/2 of 4. So we get a formal charge of 0, which we draw up here. Oh, and I forgot to draw this lone pair. Don't forget those. It's important that electrons do not disappear while we're doing this. Okay, so from there, we've got that. Now we're going to check our sulfur. Our sulfur had 6, and we know it's got 2 lone pair electrons, and it's got 3 bonds, so that's going to be 1/2 of 6. So it is going to have a charge of 6 minus 2 minus 3, that'll be +1. Then we've got our oxygen on the right, which is going to be 6 minus 1/2 times 2, because it's got 1 bond. So that is going to make it -1. You then have to do this for the second structure. And if you do, you'll find out this is -1, this is +1, this is 0. So remember our rules for determining what's the best structure. We start with, are all of them 0 for any of them? No, so we can't use that rule. Our second rule is we look for the ones with the lowest overall charges. Well, this one has a -1 and a +1 on both, so there aren't any differences in numbers, so we can't use that rule. Finally, we use our rule of we check, does it match the expectations from the electronegativities? What that means, sulfur has a lower electronegativity. That means we expect it to be the more positive if that's given as a possibility. And we expect our oxygen to be more negative because it has a higher electronegativity. Remember, you can only compare the differences between the system. Sulfur didn't have to be positive, but if it was possible, that would be better. Similarly, oxygen didn't have to be negative, but if that's possible, that would be better. So we compare these two structures, and they are exactly the same. They have one positive sulfur, one neutral oxygen, and one negative oxygen. That means we're going to say that these are equally likely. That means both answers are right in this case. So you would actually box both these answers. So both those answers are actually right in this case. And if you remember right from class, that means what it acts like is it isn't that there are half the species are double bonded on the left and half the species are double bonded on the right. Instead, it acts like there are two 1.5 bonds. It's an average between the two because they're equal. If they hadn't been equal, that wouldn't be true. They would behave most closely to the structure that was the most stable. Okay, so that's our SO2. Let's do another. Let's do our CH3F now. Okay. So now we have our CH3F again. Hydrogen can't be in the center, and fluorine is by far the most electronegative atom. So we know carbon has to be in the middle. So we have an H, an H, an H, and an F. If we count the number of valence electrons, carbon gives us 4, fluorine gives us 7, and each hydrogen, which there are 3 of, gives us 1. So that's going to give us a total of 14 electrons we need to draw. We have already drawn 8 in the bonds, so that gives us 6 left. We check the external atoms first. Each hydrogen is already happy. It only needs 2 electrons. But fluorine only has 2 and it wants 8. So we're going to start giving it the ones that we had left over. 1, 2, 3, 4, 5, 6. So we've drawn our 6 electrons, so we're out of electrons. We now check to make sure all the octets are full. Hydrogen is an exception, it only wants 2. All of them are fine. Fluorine wants 8, we've drawn 8. Carbon wants 8, it's got 4 bonds, each bond has 2, so it's got 8. So we are done with the structure. This is our answer. Except you don't draw the line through that top hydrogen, you actually put the box around it. Okay, so then finally we've got one more, which just to make room, I'm going to go ahead and erase this one. Okay, so finally we have SO3. So SO3 is going to be, as we said with SO2, sulfur is going to be in the middle because oxygen is more electronegative. Now we're going to bond it to 3 oxygens. We then have to count our valence electrons. We have 3 oxygens, each of which give us 6, and then we have 1 sulfur, which gives us 6. So we're going to need to eventually draw 24 electrons. And we currently have drawn 6 because there are 3 bonds, so we get 18. So as you remember, we start by adding them to the external atoms. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, we've drawn 18 electrons, so we're done, right? We ran out of electrons. But wait, now we've got to go back and check and see if everybody's happy. Each oxygen does indeed have 8, but the sulfur in the middle only has 6. So similar to before, we have to share some electrons. Those have to come in here. And when they do that, we will form a double bond. So we will get S, double bond O, single bond O, single bond O. And just like with the resonance structures, we have to draw each of the versions of this. Okay, so that double bond could have been in one of 3 places. It could have been on the left. I drew it again. Where's my eraser? Okay, it could have been down, or it could have been on the right. These are all 3 possible. So then what you have to do after this is you've got to calculate your formable charges again. And also you can go by and check, but each of these does indeed have 8 electrons now. Sulfur has 8 through the 4 bonds, and each oxygen ends up with 8, either through having 6 lone pairs in a single bond, or 4 lone pair electrons in a double bond. So what you do though, if you go through and actually calculate all of these, you're going to get that your formal charges 2, 4, 6. Make sure it's right. That's you a +2 on the sulfur. Not a +1. I knew I was off somewhere. Okay. So our sulfur is going to end up at +2. And each oxygen is going to, and these two oxygens that are single bonded are going to end up at -1. This will happen for each structure. And you'll end up with a 0 on the double bonded oxygen. +2, -1, -1. So from that, we again get the answer that they're all equal. So all of these are fine structures. And someday I'll get the hang of this and not write over the numbers. You can go back and look that I indeed had -1s on those oxygens. So equally likely. So all of them are good structures. So that's you go. That's all the Lewis structure examples. Make sure you're solid at these. You'll probably have to do one or a few. So now what we're going to look at is our VSPER. So this is going to be where we figure out what types of shapes we get for our molecules. So first, we always have to draw the Lewis structure. The goal of this is to figure out, okay, do we have any lone pairs or not? Because if we have lone pairs, it changes the names of our structures. And I say that because I know some people will just look at the number of atoms and come up with a shape. You will miss some of those, and I'll show you some of those in a moment. So if we have CCl4, if you go through, and I'm just going to draw the Lewis structures that are correct, but you can feel free to go through and actually do all the calculations, and you'll get the same answers as these, or at least you should. So the idea is with CCl4, we get that there are 4 atoms bonded, and that there are no lone pairs on our carbon in the middle. So that means that we have 4 bonding domains and no lone pair domains. That makes this a tetrahedral shape. And to know this, you've just got to know the big table that you've got in your textbook. The idea being that for each number of domains, you've got different shapes it can be. And then you have to count how many are bonding domains and how many are non-bonding domains. By non-bonding domains, we mean they have lone pairs. Because the lone pairs still take up space because the electrons have to be somewhere. But that affects the shape. You'll also notice that I asked for both electron and molecular geometries. In the case of atoms that have no lone pairs, the electron and molecular geometries will be the same. But if the atom has some lone pairs, then they'll be different. That's because the electron geometry is based on where the electrons are at, whether they're bonded or not. And the molecular is based specifically on just where the atoms are and how they're shaped. So the electrons don't count on us trying to figure out the shape, even though they influence us by pushing the atoms in particular directions. Okay, so then we have CO2 as our second example. And if we draw CO2, our structure ends up looking like this. I'll also note that you're not worried about which resonance structure you use, because you'll notice the number of lone pairs doesn't change on carbon, even if I made one of these a triple bond and a single bond. And the number of atoms it bonds to doesn't change either. We only care about number of bonds, not if they're double or triple. So it wouldn't have changed anything if I wasn't sure about which resonance structure was best. But what I do need to know is that there are 2 bonding domains and no non-bonding domains. That makes this linear. Again, that is the answer for both the electron and the molecular geometries. So let's look at one where that's not true, where the electron and molecular geometries are different next. So next we're going to look at water. So for water, we have H2O. And when you get it, you'll get the fact that there are 2 lone pairs on the oxygen. Note, I drew it a way you tend to see it in a textbook. It is perfectly fine if you just drew a linear oxygen and 2 hydrogens like this. And then figured out I had lone pairs and put them here. That is perfectly fine. I'm not testing you whether we know, oh, it makes this bent thingy. So now we have 2 shapes we have to answer. First, the electron geometry. This is based on the fact that there are a total of 4 electron domains, whether they be bonding or non-bonding. And that is going to be tetrahedral. But some of these are lone pairs now. So our molecular geometry is going to be different. And a system that has 2 lone pairs and then 2 bonding domains is going to be called bent. That's just something we have to know. So, if we've got non-bonding electrons in terms of lone pairs, we are going to start having things that have different molecular names than their electron geometry names. So let's look at another now. So this is a shape we don't use quite as often. But we have SF6. So it is S bonded to 6 fluorines. And what I'm going to do is I'm going to draw the lone pair slightly differently. Please, I'm going to suggest you still draw the dots. I am drawing the lines due to the complications of my pen thinking every time I make a dot, I am trying to draw a right-click circle so it gives me an options menu. Each of these represents 2 electrons. As you notice, it is slightly harder to read, and some of these look like E's, so please don't do this on your exam. I'm just doing it to make this possible here. So if we do, this is one of the shapes we had to learn, right? This is going to be octahedral. Okay, that's octahedral, and that's the same for the electron and molecular geometries because there are no lone pairs. So let's do another. We've got PCl5. So PCl5 is going to be phosphorus bonded to 5 chlorines. Again, you want to make sure that you can actually do these Lewis structures. So please actually make sure this works out for you. Don't assume that every time you won't have lone pairs because you'll notice, for example, on water we did, and we're going to have some in a moment. So this shape is something we call trigonal bipyramidal. And make sure if it doesn't make sense where I got that from, make sure to check that big table in your book or on my slides. You can also actually see from that table what the picture of this actually looks like, because sometimes for the 6 and 5 the 6 bonds and 5 bond systems especially, it can be hard to figure out what exactly this thing looks like. Why do I call it octahedral or trigonal bipyramidal? So that can help some. Okay, we've got one more to do. So let's do it. And this is an example of why we make sure that we actually do the structures. It's because this is not just going to be chlorine bonded to 3 fluorines. So first we're bonded to 3 fluorines. 2, 4, 6, 8, 10, 12, 14, 16, 18. 2, 4, 6, 8, 16. I've drawn 24 electrons. But this actually has 28 electrons, right? So we have 28 valence. We draw 6 in the bonds. That's going to leave us with 22. And when we filled up the fluorines each, we used 6, 12, we used 18 of them. So we actually have 4 left over. So we're going to have to put 4 electrons on our chlorine. So first, the electron, we do electron geometries first. It's going to be the same as our last structure for PCl5. It's going to be trigonal bipyramidal. But then we had to figure out, okay, so what is our molecular geometry for something that looks like this? And if you remember for our list, this is going to be something that is T-shaped. And that is because, since it is trigonal bipyramidal, that means we take the 2 lone pairs are going to form on the equatorial plane. That means we have 2 fluorines that are in the axial plane, and then 1 that's left in the equatorial. This ends up making a structure that looks like a T. So if I were to more correctly draw this also, once I knew the shape, and you don't have to do this to draw your Lewis structure, it's fine if you left it like you did, but the true answer is that it looks something like this. Okay, those lines shouldn't be bent. I'm just not very good at drawing, to be perfectly honest. So, we need to get something where 2 of the fluorines are up and down and 1 is to the side. That's what makes it T-shaped. And again, sorry about the lines. This is just so I don't have to try to make that button come up. So having done that, that's really all there is for Chapter 6. So Chapter 6 does have some learning to do in terms of learning the shapes, learning how to do Lewis structures. But once you've got those, you've got 80% of the chapter, maybe even more. Maybe we're like 90%. The only other thing to worry about in this chapter is that stuff at the very start where we worry about the definitions of types of bonds. So the stuff like ionic and covalent and polar covalent, as well as the stuff about what electronegativity is. And just a little bit from that then about, okay, so what is bond polarity? That thing where we drew this structure here to point out this side was a little bit negative and this side was a little bit positive. But other than those couple things, most of it's just these 2 parts, drawing Lewis structures and doing shapes. So that will get you through most of these questions. You'll also notice that to do the shapes, you have to be able to draw the electron Lewis structures as well, because if you couldn't do that, you would not have been able to get that the structure was T-shaped. You would have probably guessed that it was trigonal planar because it was connected to 3 fluorines, and just assumed, oh, there must be nothing else. There probably are no lone pairs, because that's how he does it. Okay. So hopefully that was helpful, and I wish you luck on the exam.